I'm going to start. I'm going to start. Should I admit? Okay. So I'm going to talk for like 10 or 15 minutes. It's actually surprising. So I came in 1999. So I actually been here for 23 years. And so we started in robotics in 91. And then I've been here since 1999. So I'm going to talk about robotic exoskeletons a bit. Please stop me at any time. So the objectives are to think about the roles of exoskeletons. They could be used for injury prevention, rehabilitation, assistive devices, chronic care. So personally, excuse me, if you go on the website, if you go on to asu.edu, you can see that we built exoskeletons to help the Air Force load cargo onto C-17s. So I'll discuss different types of exoskeletons and some of the common terminology so you can just kind of understand this area. So why exoskeletons? Well, the big problem is we're in the age of decay. So some professors that I work with at University of Arizona talked about human beings died of death, died from disasters. Then they died of disease. Yes, obviously right now we have disease as well, but decay, meaning the body wears out. So you have heart disease, you have stroke, you have non-communicable diseases have become the leading cause of global mortality. So people are getting older. So especially in Asia, but also in the United States, people are now living a lot longer. So people want and expect mobility in their 70s, 80s, and 90s. And I can give these slides to Professor Redcar. And so as we age, we need to walk. So if you sit, like we're all doing right now, sitting is the new smoking, you have twice the risk of diabetes, cardiovascular disease, and it's hard to walk. So, excuse me. So why wearable systems then? People are getting older, but they are living longer with higher expectations. Humans want, but also you need mobility, you need to be able to walk. And now microprocessors, sensors, batteries, everything like that are making exoskeletons possible. And so exoskeletons are in the rehabilitation area, industrial area, military area, and recreation. So I'll give you some examples. In rehabilitation, people are building devices for stroke. For assistive devices, people are building devices for spinal cord injury. So you need to get up and walk after spinal cord injury. People are doing logistics exoskeletons for the car manufacturing plants. We just hosted Exo Workathlon. That's why I'm a little tired. Exo Workathlon was in Germany this week, started at midnight and ended at 6 a.m. the last 3 days. And in recreation, people are building exoskeletons for like soccer, so you don't twist your ankle. Or people are building exoskeletons for skiing, so they can ski better. Okay, so we're going to go quick here because I don't have a lot of time, but spinal cord injury exoskeletons were the ones that came out earliest. These are expensive devices, FDA approved medical devices. So Indigo came out of Vanderbilt, Exobionics, Berkeley Bionics, Rewalk came out of Israel. These are the biggest ones, Rex Bionics out of New Zealand. So you have systems that typically power the hip and the knee. The ankle is typically passive, and you are able to get up and walk after a spinal cord injury. In rehabilitation, there's devices after you had a stroke. So this is probably the most famous device. It's an exoskeleton that is mounted to a treadmill system, but it is the loco mat. And it is an exoskeleton system that helps to retrain you to walk. Because just like on anything, if you have a brain injury, you need to retrain your brain and take a lot of steps, right? So you need thousands of steps to retrain the brain. You can imagine it took you a year and a half to learn how to walk, right? So you did thousands and thousands and thousands of steps when you were a baby. But you forget that, but you needed that. The other famous ones are there's systems which you manipulandums out of MIT. That's an interactive one where you move your arm back and forth and you reach for targets and try to retrain your upper arm. Rehabilitation, we are right now building an elbow. This is one out of MIT again, but we're building an elbow exoskeleton with the Mayo Clinic to build devices. But people are thinking about exoskeletons for knees. How many times do people have artificial knees, or it's hard to walk, it's hard to go up and down stairs, right? So people are building systems for that as well. Honda, so then you can imagine systems are also just to assist daily living. So Honda has a walk assist device that has motors on the left hip and the right hip to assist walking. You can imagine a walking chair. So people are making chairless chairs where you can walk around, sit, do your manufacturing task, and then walk somewhere else. People think of these large powered exosuits like Iron Man and all that. Those typically are kind of bigger, bulkier, and kind of too expensive right now. People are doing, and I'm just trying to give you guys a feel for what's out there. People are building soft exoskeletons with pneumatic devices. So think about the work that Dr. Wenlong Zhang is doing in soft robotics, right? So people are building soft actuators, right? So it doesn't have to be these rigid motors. And in fact, the rigid motors are tough because you got to get them at the right spot on the hip joint and make them work properly. Has anyone worked with some of the soft robotics? You guys know what I'm talking about? Good. So the soft robotics is a new area. The only disadvantage of them is how do you get that pneumatic power source, right? But Inafis out of Japan has a soft robotics device. There's things out of Korea. There's things out of Canada, in Sweden. All the Batimia is a knee device that is being used for stroke therapy, but it's also the Batimia device. They also have the Onyx device with Lockheed Martin, so a military device. Okay, a couple more people. This might be the most famous company in exoskeletons. Cyberdyne. It comes from, those movies. They have HAL 1, HAL 2, HAL 3 robots. So they've got exoskeletons out of Japan. Korea's working on it. Toyota, Japan, Hyundai, Korea as well. So people are all trying to build exoskeleton devices. So what do I think about exoskeleton devices? I think about you have to have motors at the right place. You have to have sensors, you have to have batteries, but the most important thing I spend most of my time on is how do I understand the human intent? So if the person wants to walk and then stop, and then walk and then stop, a really difficult task. I've been using phase angles. Dr. Redcar does a lot of specialty work in this area, using, studying the sensors, doing IMU sensors, and studying the human motion. So the goals are to seamlessly interact with the user, not disrupt the gait cycle, pay for the weight penalty. Probably 95% of the exoskeletons out there makes it feel like you're walking through water. So it makes, so it actually is an exercise piece of equipment. It's not supposed to be, but it's an exercise piece of equipment because it's actually harder to walk with the device than no device at all. People don't want to think about it, they just want to walk. And so it's a tricky task. So as I said, most devices are too bulky, too heavy. Most devices impair the trunk motion. Most devices just use standard PID controllers. We use positive feedback controllers. So types of exoskeletons, some can follow the joints, so they're anthropomorphic. The problem with that is this has to be aligned with the ankle, aligned with the knee, aligned with the hip. This one is aligned with the knee, is aligned with the hip and the ankle and not the knee. We built devices like this as well. This is RB3D out of France. Some devices are active, so you have active motors. Some devices as mechanical designers, you could think about building spring systems that are constant force mechanisms. So these systems have an advantage. You don't have to turn the motors on and off. The disadvantage is the spring really helps you for some tasks and it's in your way for other tasks. So yes, Dr. Redcar and I are thinking about quasi-active systems when you turn springs on and off at the right time versus, motorized systems. So here's a Cyberdyne lumbar system being used at an airport in Japan. Some devices transfer the load all the way to the ground. In fact, we found the joint ones to be the best so far. Soft exoskeletons, probably the group that's getting the most publicity is Harvard doing soft exoskeletons. They call them exosuits. So you can imagine soft pneumatic systems going up and down the legs or up and down the arms. So here's a picture of their latest system. It's not so soft, I joke around, because you have a big waist belt with all the motors. You have bicycle cables, they're called Bowden cables, coming down, and then you're pulling, on the joints. But that's their latest work. Some systems, are more rigid. People are trying to go to more jointed systems. What we did in the past, we built, this was back in like 2002 and 3, we built soft exoskeletons for the arm for stroke rehabilitation. This was called Rupert. We built a foot mentor to assist the foot after a stroke, a hand mentor, and then a soft system. Here's just a quick point. The soft people, and this is again, as engineers, you have to think about these things. These soft systems look great. They're simple to put, but they put compressive load. When you pull on this pneumatic system, you put compressive loads on the joints that never were supposed to have compressive loads. So that's why we had a pneumatic system connected to an exoskeleton shell so that the wrist did not have compressive loads, because people were getting, pain in the wrist, using some of these soft systems. So please think about that. What have we done? We built robotic orthoses since 2004. We stopped in about 2010. We built prosthetic ankles. We built exoskeletons. Also, remember this, you can give the person help without power. This is a new area. How can I give the person help even though I don't have a motor. So when the leg rolls over the ankle, the muscle has to resist. People didn't realize that it takes a ton of energy for you just to stand up straight and for you to resist gravity. So if I put a spring on here with a clutch and turn the clutch on and off based on heel strikes on a treadmill, I can make the leg do less work. And they showed reduction in metabolics or reduction in energy usage just with a passive system. And it was so important that it made nature. People are also thinking about exobracing. So maybe after an injury and you're in the hospital, they'll brace you up with something and then adjust that brace later on. Why is that important? It's important because if I immobilize your arm for 6 or 10 or 12 weeks, lots of the muscles, what do I want to say? They deteriorate. I was going to say deteriorate, but that's not the right medical term. Atrophy, thank you. The muscles atrophy. And maybe what you want is a brace that holds part of the arm, but not the whole arm or part of the leg. So I went fast, but I want to still maybe show you, let me show maybe a video or two. Do I have time for a video, Mr. Rebecca? So let me just see if I can quickly show a couple of videos of kind of where we got. Let's see, Sparky, robotic. This was from like 2008. We did all of this using the people from my previous class. We did all of this using microchip stuff. So literally this robotic ankle is completely autonomous. Let's see if I can make it bigger, right? Do I make it bigger here? So that bridge is really hard to walk on. So go to Tempe and try to walk on that bridge. So this is,
I just have that feeling that it just wants to carry me. It feels so much like my normal leg, like my natural leg, and how much walking used to feel like before I lost my leg.
Let me pause, play again.
And so in that respect,
I'll let you guys watch. It's much better on my, it's actually good on the here. So we'll stop there. Let me do one last video. So lately, we're proud of let's see, Air Force exoskeleton, ASU. Let's see a video. Oh, I'm not going to play the whole thing because we don't have a lot of time, but this was just maybe 6 weeks ago. So we had to be at the Air Force for 8 weeks. We were loading PPE and COVID supplies onto C-17. So I'll stop there because I think, is that good, Professor? Well, let me take some questions and then, yes. The Marines, so people did build robotic devices for Special Operations Command. The problem there was the device has to be super quiet, last for 72 hours and things like that. That's a hard sell, but there is some there. I mean, I think I'm still there. I can, people are working on it. Onyx, exoskeleton. I think that robotics for logistics is going to come quicker. But here's a knee device. People are working on.
And all I had to worry about was ensuring I had.
So it's a device to help the knees while carrying heavy loads. The Onyx will be one that they're doing for special operations. We did some work there. I did, since you guys asked the question, I mean, I've done a lot over the years. So he said exoskeleton. This exoskeleton images was to help you carry 40 pounds of armor. So you're wearing armor and it's helping. What? Yeah, it was to help you with an IOTV vest. So it had armor plating, front, back, sides. So we built that at ASU. Other questions? So right now I don't have any particular openings, but we can, chat and talk and things. I'm going to stop share there, but yeah, we've been building because some of it is trickier because if I have a
Okay, so based on popular demand, today I am going to cover the inverse kinematics. And let's work out the problem that I assigned you for inverse kinematics. Right? Okay, how many of you have solved the problem? All right, come on, open up your laptops, computer, and tell me the homogeneous transformations. Let me set up the problem. So idea is, I asked you to build a cardboard robot arm. So the assignment is building a cardboard robot arm, and step 1 is to draw the kinematic diagram. So I'm going to draw the kinematic diagram, and so correct me if I'm wrong. So what we have is we have a revolute joint. then that revolute joint is attached to another revolute joint, and the kinematic diagram may or may not be similar to the actual physical robot, but it should convey the basic idea. So you have something like this, and then you have another joint, which is, or I can just draw something like this. You have another joint just like this. You agree with me? And then you have something like this, and this is where your gripper is. Now the question that was asked, so where should I consider the end effector? To be honest with you, for me, it's an open-ended question. If you want to consider the end effector here, this is your end effector, that is fine. If you want to consider your end effector over here, because please understand that the gripper, the revolute joint of the gripper, the only purpose of that revolute joint is to grip an object. It's not adding any articulation. That articulation is needed so that you can grip an object. So you can write something like this. Then this is your first revolute joint. This is your second revolute joint. This is your third revolute joint. Do you agree with me? Then you will have your kinematic diagram. By the way, you know that this problem is actually solved and solution is uploaded on Canvas, right? Okay.
The forward is solved because
so I don't remember the coordinate system that I used here, but I'm just going to assume a coordinate system. Z0, X0, Y0. This is Z0, and X0 should, X1 should intersect. This is Z1. Z1. X1 should intersect Z1 and X0. So this is X1. And then what you have is this is Y1. Okay. Yeah, sorry. This is correct. X1. Now same thing over here. Z2, Y2, X2, and the last Y3, X3, Z3. Is this correct? This is the same coordinate system that I used. Now, one thing that you want to understand, that this is your theta 1, this is your theta 2, and this is your theta 3. You agree with me? Please note, your physical robot may not be able to achieve this kinematic configuration. Even though I have drawn the kinematic configuration like that, robot fully extended, your robot in actual practice may not be able to achieve this vertical first link and horizontal second link. But that's okay. It does not matter. For kinematic diagram, everything should be in stretch and extended position. But the question that comes in mind, and this is very important, the question that comes in mind is, how do you measure the distances? So for an accurate analysis, how would you measure the distances? So what I always tell students, is measure for the kinematic diagram, measure the vertical and horizontal projections. For kinematic diagram, measure the vertical and horizontal projections. So you would physically measure the center to center distance between the first or the zeroth and the first joint, vertical direction, horizontal direction, and determine these dimensions. So I'm going to call this maybe A1. I'm going to call this A2. And then I'm going to call this A3. So imagine if you were to stretch your robot in this particular orientation, what would be the distances? Those are the distances that you should use in your homogeneous transformation. Everyone understood this? Any questions here? Now, yes.
So we measure it's likely to stretch out even if it physically can't stretch out.
Right, right. Even though the robot, you cannot physically break and stretch out, but still what you should do is you should look at the projections. That will make your life a lot easier. Yes.
Just to clarify, so you're saying measure length overall, not like from one joint to another?
One joint to other joints. So basically identify the joint axis of rotation.
Okay.
And measure, say for an example, your vertical axis for the first joint is over here. And clearly, this is what's going to happen. In the actual robot, the second joint is never going to be on the top of the first joint, right? It would be slightly away.
Right.
But what I'm saying is measure the horizontal and vertical distances between those two joints.
Okay.
Because that is what we are representing in kinematic diagram.
Right.
Everyone understood this? Okay. Now, I'm not going to derive the homogeneous transformations because I assume that by now you are extremely proficient in deriving homogeneous transformations. Oh, wow, good. Rules are 4 rules observed in this. Yes. So now what I want from you, and this is super important, what I want from you is the final homogeneous transformation equation. So this is your frame 0, frame 1, frame 2, frame 3. So 0h3 is equal to 0h1, 1h2, 2h3. So everyone understood you have to look at the rotation matrices, the projection matrices, all that stuff. If you want, you can use DH parameters. Whatever you do, final answer has to be the same. Okay. So now tell me 0h3. I know it's a long expression. Tell me first row, first column.
Cos theta 1 plus cos theta 2 plus 3 theta 3.
Cos of
Theta 1.
theta 1 plus theta 2.
Multiply by or get.
I was not planning on solving this problem, but since you asked, theta 2 plus theta 3 cosine theta 1 minus sine theta 2 plus theta 3 cosine theta 1. And then you have sine theta 1. And then you get expression. I'm going to call this px and I will write px separately. Okay. Second, you are going to have cosine theta 2 plus theta 3 sine theta 1. Then you have minus sine theta 2 plus theta 3 sine theta 1 cosine theta 1. You have py. And then you are going to have sine theta 2 plus theta 3 cosine theta 2 plus theta 3. I think you have 0 here. 0, 0, 0, pz and 1. And now I'm going to write down the expression for px, py and pz separately. So px is going to be cosine. This actually is a very simple problem. Cosine theta 1 a3 cosine of theta 1 theta 2 plus theta 3 plus a2 cosine of theta 2. Py is equal to sine theta 1 a3 cosine theta 2 plus theta 3 plus a2 cosine theta 2 and pz is equal to a1 plus a3 sine theta 2 plus theta 3 plus a2 sine theta 2. Did I miss something?
In chat. Yeah, negative cosine.
Here,
The second row and third column.
third column, second row, this guy, right?
Yeah.
No, your answer is right. I copied it wrong. Okay. Okay. What was the question from online? Okay, yeah. Okay, so okay. So, can you see just by looking at the equation, if you take ratio of py divided by pz, that is going to give you theta 1. I don't know what the discussion is online. Is this homogeneous transformation correct?
Yeah.
So what do we have to find out? We have to find out theta 1, theta 2, and theta 3. Everyone agrees?
Yeah.
Okay. Actually, there are some shortcuts that you can take here, but let me start with the basic, super basic example. So let's assume for inverse kinematics, Px is known, Py is known, Pz is known. So what you can do is, you can see tan theta 1 is equal to Py by Pz, Py or Px, Py by Px. The cleaner way to solve this is A tan 2 Py comma Px. Now with that, please note theta 1 is known. Now let's go back to the equations again. And what do we have? Well, so think about it. So this equation Px cosine theta 1 is known, sine theta 1 is known. I want you to focus on these two equations, and I will need some help copying this equation down. So the equation that I'm looking at is Px divided by cosine theta 1, because theta 1 is known now. Cosine theta 1 is equal to, what is the equation on the right hand side? A3, yeah, A3 cosine theta 1 plus theta 2 Theta 2 plus theta 3. 2 plus theta 3. A2 cosine theta 2. Now please understand, if you do the exact same thing for Py, it does not give you any more information. So if you do Py divided by sine theta 1, that gives you the same right hand side. Do you agree with me? So that equation is not useful. But we are going to go to PZ expression. PZ expression is given as PZ minus A1 is equal to PZ minus A1 is equal to A3 sine theta 2 plus theta 3 plus A2 sine theta 2. Everyone understood this? Now, please note, this is the exact same case that I solved in last class, wherein the right hand side is completely known. And I want to eliminate one of these terms. So which term would you eliminate? Always remember to eliminate the term that contains two or more angles. So what I'm going to do is, I'm going to take A2 cosine theta 2 on left hand side, A2 sine theta 2 on the left hand side. So please note, this is known. So can I call this maybe A? Can I call this B? So this expression is going to look like, because A is known, A and B known. A3 is known, A2 is known, A3 is known, A2 is known. So I would do A minus maybe A2 cosine theta 2, B minus A2 sine theta 2, and on the right hand side I'm gonna have A3 cosine theta 2 plus theta 3, A3 sine theta 2 plus theta 3, and then I will square on both sides and add. So my expression is gonna look like A minus A2 cosine theta 2 square plus B minus A2 sine theta 2 square is equal to, when I square and add on the right hand side, I get A3 square. Do you agree with me? So this equation, this guy is known. Please note, A is known, A3 is known, B is known, A2 is known. So what we do now is expand. You want me to solve the problem, or everyone is comfortable how to solve the problem from this point onwards? Huh?
Can you continue on forward, please?
That is like giving you the solution of the assignment. The next thing I know, next thing, can you show us how to solve this on MATLAB? Yeah. Then can you upload the MATLAB script on Canvas? And tell me, when is this assignment due? Saturday. Okay. Okay. A square minus 2A A2 cosine theta 2 plus A2 square. What?
He said, can you do the final for us too?
There is no final for this.
That's the final.
Yeah. Anything else? So B square minus 2B A2 sine theta 2 plus A2 square sine square theta 2 is equal to A3 square. Now, one thing to observe very quickly, this guy, they get added. A square, B square is a constant. A3 square is also a constant. So all said and done, remember, you are gonna get an equation. That equation is of the form, I don't remember the constant that I used, but that equation is of the form, I'm gonna call it A bar cosine theta 2 plus B bar cosine or sine theta 2 sine theta 2 is equal to C bar. You agree with me? And what is the next substitution? Is the half angle formula, right? So you would substitute the half angle formula and then you will get a quadratic equation. Once you solve that quadratic equation, you are gonna get two values. So two values for theta 2. Everyone understood this? Okay. And then once you find out those two values for theta 2, you would plug them in this equation. So I'm going to call this equation 3 or equation 4. And then that will give you the value of theta 3. So theta 1, we found out earlier. Theta 2, we got from this expression. And from theta 2, we are going to find out theta 3. Everyone understood this? That is how you will solve inverse kinematics problem. Yes, question?
So going from the green line to the pink line, so you squared both sides and added them together, correct?
I squared and added, yeah.
What happened to the cosine of theta 2 plus theta 3 on the right?
So sine square theta 2 plus theta 3 plus cosine square theta,
Okay.
it becomes 1.
Thank
You're welcome. Now, if you want, there is something you can do at this point. You can use MATLAB solve, and sometimes it may give you good results. But the problem with that is because of the floating point arithmetic, it may or may not give you good results in certain cases. So it's always a good idea to do hand calculations to see what the values are, and then you are welcome to check those answers with MATLAB. Everyone understood this? Now let me talk about the second question, a workspace. Let's physically, have you built the robot? Okay, good. So then this is how the robot looks. And I'm going to show you just something like, this is a small revolute joint. Then there is this link. And then there is this link. And then there is this gripper. This is how your robot looks like. Now what I want you to do is, let's look at the workspace of this robot. What do I mean by workspace? Workspace means all possible positions that the robot can reach. Now, in the example, in the question, it asks you, state whether the particular position is achievable or not achievable. There are multiple ways of doing that. First and foremost, look at Px, Py, and Pz. As long as Px, Py, and Pz are inside the workspace of the robot, that position should be achievable. Now, what does that mean? Is imagine if this robot is mounted upside down, then the workspace or the points that robot can reach would be different. But you can assume the robot to be placed on a flat surface and physically, and I don't know what you consider as end effector, but for my calculations, if this is the end effector, I would move the end effector to all possible positions. So it seems to me that based on this configuration, there is a maximum radius and the minimum radius that the end effector can reach. So this is the center line. This is the center line. This is the maximum outside reach, R max. And this is the minimum outside inside reach, R min. And then this robot, and again, you have to physically see, potentially can go from this height to this height. And depending upon how your robot is, it could be a purely a cylindrical workspace, or it could be like a trapezoidal workspace, or it could be sort of a cone, cutout cone. So it totally depends upon how your workspace or how your robot is built. Then what you should do is, given the value of Px, Py, and Pz, you should find out whether this point lies within this workspace or not. So for an example, this is the outer cylinder. This is the inner cylinder. As long as your Px, Py, and Pz are inside this workspace, or also called as the cell of the robot, then you would say that's a feasible solution. Potentially, once you do the inverse kinematics, your mathematical equations will give you two answers. So for an example, this is a perfectly valid configuration. Also, this is a perfectly valid configuration. So what now? In that case, what you want to do is, you want to physically constrain the values of theta 1. So theta min, theta max. Then theta 2 min, theta 2 max, theta 3 min, and theta 3 max. And you want to make sure that the solution that you obtain is within these boundaries. Everyone understood this? Yeah, question? Yeah.
We can measure it out physically.
You can measure it out physically. Question?
So, yeah, on the top of that only, because of our, if you forget about the actuation, the robot can make a lot of movements. The robot will do it. But like, because of the syringes, it's only moving like 20 degrees at a time.
Correct.
Should we take the workspace as that?
Yes, you basically, because you're actually, and that actually happens in physical robots too. Even mechanically, with the joints, robot would have a lot more mobility. But once you add actuators like cylinders, once you add motors, they have their own limitations. So the mobility of the robot is restricted. So that will happen in a lot of practical robots. So once you put everything together, just see what is the mobility region for the robot and use that to find theta 1 and theta 2. And then when you actually upload, then find a position that is clearly achievable, and then find the inverse kinematics and show it. So yeah.
Okay, so for this, you showed, I guess, a cylinder with a smaller cylinder cut out of the
Uh-huh.
inside, but the robot can't actually, because of how the base is actuated with the cylinder, it can only move like 10 or so degrees. I don't know
Yes,
exactly what it is.
correct.
Do we have to take that into account for the first axis as well?
Yes.
So we have to mathematically make an actual like pi out of it.
No, you don't have to make mathematically. You can just measure the robot, physically move the robot, measure what is the maximum theta 1 it can reach, what is the minimum theta 1.
Okay, so for the cell, we don't have to take that into account, but for the theta 1, theta 2, and theta 3, we do that. And then
Correct.
it works out.
For an actual robot, that's why you have an actual robot in front of you.
Okay,
So you can actually measure.
thank you.
You're welcome. Okay. Any other questions?
This is for position, right?
What?
This is for the position, right?
Yeah. Everyone comfortable with positions? Okay. So in next 5 minutes, I'm going to teach you. Actually, I don't have to teach you. You already know. I will just make you aware that you know. So, Robotics is more common sense than anything else. So, is there a final? No final. A degree. Okay. So I would encourage, if you like what you are seeing in robotics 1, to take robotics 2 and think about 4+1 program if you are undergraduates, or think about taking additional classes in robotics like foldable robotics, automation and other systems classes at Polytechnic campus. I'm trying to add some more interesting classes. Yeah.
I was just gonna ask, did you determine the orientation capability at the same time?
Okay, or actually orientation is super simple. Since you asked, nobody caught my mistake. Is it 1 or 0? Okay. So now here is the issue with orientation. So for this particular robot, question. Oh. For this particular robot, now how would you identify the orientation? Now this goes back to the discussion that we talked about. So for an example, I did not specify an orientation, but what I want to do is I want you to give me an orientation at the wrist. But look at the wrist configuration. Based on how the wrist is, there are 3 possible orientations, 3 main orientations. First of all, think about like you have a spray can. So your spray can be something like this. Your spray can be in this orientation, or your spray can be coming out. So essentially, when I specify the orientations, the principal orientations are, it could be in this direction, it could be in this direction, it could be in this direction. Do you agree with me? Now, some of you may wonder, what about which is inclined, somewhere over here, inclined? This inclination is fine, but at this point, I want you to understand the clear difference here. If my spray can is inclined at the axes that are shown in purple, it will continue to maintain the orientation. There is no articulation of the spray can about that axis. You see what I'm saying? In other words, if there is some non-standard orientation, you can resolve that orientation in terms of its body fixed coordinates. Everyone understood this? Easier said than done. How would you do that? Okay. So let me start with a simple case first. So what you have is, say, imagine, we'll start with something like this. So think about the way the problem is set up. So your spray can, for this matter, for this discussion, spray can is like in this direction. Oops. Spray can is like this, and this is where the spray can is. So you have your gripper, something like this. Now what I want to do is, based on this orientation, I need to find out 0 R3. So what is 0 R3? And please remember, DH parameter does not give you this insight, but rotation matrices always. So what is the physical interpretation of 0 R3? Whenever in doubt, write the coordinate system: x3, y3, z3, x0, y0, z0. Can you see x3 is aligned with x1, x0, 1, 0, 0. Y3 is aligned with z0, and z3 is aligned with -y. Do you agree with me? So if you want your robot to spray in front, and here is something that I want you to think about, that this orientation can remain the same even though the robot goes forward or robot comes backward. As long as that spray can is in this orientation, your 0R3 is going to be like this. Now you have this 0R3 matrix. What we should do now is we should compare this with 0R3 from your homogeneous transformation. So if you look at your homogeneous transformation, can you see that? And this is minus cosine theta 1, right? For this orientation, minus cosine theta 1 is minus 1. So I can say cosine theta 1 minus cosine theta 1 is equal to minus 1, and then theta 1, can someone tell me what would be the value? 0. 0 degrees. Now you would use this information and then find out, but here is what usually happens. Because of the properties of the homogeneous transformation, once you do the inverse kinematics, the angles that you get will automatically satisfy the rotation matrices relations. So that is going to happen all the time. So just play with these equations and then you will see once setup is right, the equations will work out themselves.
Actually, worry about the orientation. Code.
In this particular problem, orientation is not that important. I'll tell you the reason why. Why orientation is not so important? Because the orientation capabilities of this robot are limited. There are only first 3 joints. First 3 joints are primarily responsible for position. What does that mean? It means once you find out theta 1, theta 2, theta 3 corresponding to Px, Py, and Pz, your orientation problem is solved. Remember the 6 degree of freedom problem that we solved? Now imagine a case that if I add 3 more joints later, then what you need to do is, remember, from this theta 1, theta 2, theta 3, you have to find 0R3 in a numerical form. Transpose it, multiply that with 0R6 and solve the inverse kinematics problem for 3R6. All.
The thing which you did that we should.
Yeah.
Yes.
Everyone understood this? That is how you will solve the. Do you want me to write it down or everyone okay?
Can you write? I didn't catch that.
Yeah.
The normal matrices that were read.
Okay, so now imagine that at the end of this robot. So for a 3 degree of freedom robot joint, 3 degree of freedom robot is a manipulator. If I give you Px, Py, Pz, you can find out theta 1, theta 2, theta 3, theta 1, d1, d2, theta 1, d1, theta 1, d2, and theta 3, something like that. So for once the position is given, first 3 joint variables are completely known. Now the problem is you add a spherical wrist. So if there is a spherical wrist, say 3 joints, then you agree with me, you are going to have 0R6. Once you have a 0R6, either from roll, pitch, and yaw, or from the rotation matrices, you need to find out. So X6, Y6, C6, X0, Y0, Z0. You need to find this out. This will be known. Agreed? You would solve the forward kinematics for the whole manipulator and know 0H6. Now here, the issue that you will have is this 0R6 will be in terms of theta 1 all the way to theta 6. Do you agree with me? This will be having theta 1 to theta 6. Now, what has happened from the manipulator inverse kinematics from IK of manipulator, which means Px, Py, Pz given, you can find theta 1, theta 2, theta 3. Do you agree with me?
Yeah.
So this problem can be written as 0R3, 3R6 is equal to 0R6. Now, some of you may ask me what is happening here. So this is what is happening. So this known guy is over here. 0R3 can be found out from here. Now the question is, how do we find 3R6? To find 3R6, what you will do is, you will have 0R6. Please note, this is in terms of theta 1 to theta 6. What you can do is, here, substitute the values of theta 1 to theta 3, which means the only unknown in this expression is going to be theta 3, and theta 4, theta 5, theta 6. 4, theta 5, and theta 6. And what you would do is, by term comparisons, you can find out the value of theta 4, theta 5, and theta 6. That's what I did in the last class, and the video was uploaded. Yeah.
0R3 is not always orthonormal, right?
0R3?
Is 0R3 always orthonormal matrix?
0R3, all the rotation, this is the condition for rotation matrix. For any valid rotation matrix, it has to be an orthonormal or unitary matrix. Orthonormal means unitary. Inverse is equal to transpose. Everyone understood this? All right. Now what I'm going to do is, I'm going to try this. I'm going to try to finish one entire chapter of robotics 1 in 5 minutes. So everyone, please pay attention. Okay. Everyone pay attention. So in the last class, remember we talked about, or why last class? For that matter, this class. So remember, we have this expression. This expression is, I have an expression for Px, I have an expression for Py, I have an expression for Pz. These are the displacements. Now, if I want to find the velocities, what I would do? I would differentiate and use the chain rule. Everyone understood this? I differentiate and use the chain rule. And that is all there to it for the velocity analysis. So what I'm going to do is, so actually I wanted to extend this on the problem that I solved with a spherical wrist. So this is the problem that we solved in last class. Because the orientation, rotational velocities come out very nice. You can explain it very nice in this problem. So if you have the notes from the last class, this was the manipulator that we solved. And the equation, this is super important, equation for Px was A3 plus D3 cosine theta 2. So if I want to find out the velocity, I need to differentiate this. So I'm going to write this down. A3 cosine theta 2 plus d3 cosine theta 2. Px dot a3 is a constant. Derivative of cosine minus sine theta 2. But we have to use the chain rule because it's a function of a function. So I have cosine theta 2, but theta 2 itself is the function of time, and I am taking the derivative with respect to time. So I need to multiply this guy by theta 2 dot. Everyone understood this? I'll write this down here. Cosine theta of t d by dt is equal to minus sine of theta of t multiplied by d theta by dt, which is minus sine theta multiplied by d theta by dt, which is minus sine theta theta dot. Everyone understood this? Okay. Now let's look at the next part. U multiplied by v, because d3 depends upon time, theta 2 depends upon time. So this is gonna become d3 dot cosine theta 2 plus d3 minus sine theta 2 dot. Do you agree with me? Same thing for py. Py is given as a3 plus d3 sine theta 2. So when I do this, I will go quickly a little bit here. This will become cosine theta 2 dot plus d3 sine theta 2 plus d3 cosine theta 2 dot. Pz is d1 plus z1. D1 plus, I think it's a1, right? D1 plus a1. When I take the derivative, pz dot is going to become d1 dot. Now I can write down these three equations: equation 1, equation 2, and equation 3. Yeah. D3 dot, yeah. D3 dot. So what I can do now is I can write, and this is very important, px dot, py dot, pz dot. These are the velocities of the end effector multiplied by a matrix multiplied by the joint velocities, which is theta 1 dot, d2 dot, theta 3 dot. And px dot is theta 2. So this is theta 2 and this is d3. So now what you can do is you can did I do it right? Let me see. So d3.
There's no theta.
No, actually this is
D1 theta 2.
d1. So d1 dot. No, d1 dot is correct. A2, d3. So what you would do is your variables are d1 dot, then you have theta 2 dot, and then you have d3 dot. So you can write this expression, and this is called as the Jacobian. And that's all there to it for velocity analysis. And then if you want to find out the orientation or the angular velocity, that is even super simple. Omega x, omega y, omega z is equal to the only rotation that is possible is over here. You agree with me? Theta 2 dot. So it is given as 0 r2 0 0 theta 2 dot, and that's it. So you would notice 0 r2 is the rotation matrix that relates the 0th frame to the 2nd frame, and now theta 2 dot, this is very important, our joint axis is always going to be z, which means theta 2 dot will always be around z axis. That's why you can see this 0 0 theta 2 dot. Once you expand, your orientation angular velocity problem is solved and the linear velocity problem is solved. Next class, I will work out problems. That's it for today. Yeah. Today I have all students coming also. So